Yes, Bismillahirrahmanirrahim. So welcome everyone to the first class, inshallah. The previous one we have, I have presented the course outline for this semester. You may follow that the important things from the Tuesday class is that the assignment will be released early so that you can work on the assignment before any other assignment. As this assignment is important, this is measuring your graduate attributes, okay, measuring your PO, okay, PO number one, engineering knowledge, of course, specifically for OS. Engineering number two is, PO number two is problem analysis, and PO5, which is the modern tools, okay. So that's why also don't wait, please start to learn RAS, okay. The video lecture is already there on the iTalib. Okay, so I also for the chapter one, there are some 6 learning outcomes that we want to achieve, okay, by the end of the chapter. Okay, so this one that will contribute to the learning outcome of the course and then contribute to the PO or program outcomes. Okay, so if you don't know this one, all the quizzes, all the midterm will be based on this one. Okay, will be based on if you can answer or describe from the study guide here, then you have mastered the chapter, that particular chapter. Okay, inshallah. Okay, so the first learning outcome for this one, for the chapter one, which is the computer system overview. This is the continuation of your computer architecture, okay, on year 3 courses. The first one is describe the basic element of computer system and their interrelationship, and explain the steps taken by a processor to execute an instruction. Understand the concept of interrupts and how and why a processor uses interrupts. Okay, and describe the level of typical computer memory hierarchy. And then number 5, explain the basic concept of multiprocessor, multi-core organization, and describe the concept of locality. Okay, that we use for the cache memory. Okay. Yeah. So the first number one, the basic element of computers, as you know, the von Neumann machine. We have CPU, we have memory, we have I/O, CPU, memory, I/O. Okay, and then in the bus to interconnect all the 3 components. Okay. And explain the step taken by processor to execute an instruction. Basically, it is fetch and execute. So you fetch the command and then execute. Okay, so if you go to assembling language, the instruction will be either fetch and then do some operation and then put it back on the memory. Okay, and then fetch, execute every line, and you will fetch and execute. So in the case it will be serial, but in the case of multiprocessor, then you can run 2 instructions at once. Okay, 2 or more instructions at once. Okay, and then number 3, understand the concept of interrupts. So the main idea here is that the I/O part is rather slow. Okay, so for example, the hard drive, okay, in your computers. Yeah, so the hard drive in your computers is 100 times slower than the memory. Okay, 100 to 1000 times slower than memory. Okay, so that's why we need to interrupt. While we are waiting for the I/O operation to finish, we can do some other works. Then when the I/O operation finish, then we can interrupt the processor to continue our previous work. Okay, so that's the idea of interrupts, to make efficient use of processor utilization. And then list and describe the level of typical memory hierarchy. So the hierarchy, of course, you have the one that's closer to the CPU. Okay, closer, faster, smaller. Okay, and more expensive. Okay, closer, faster, smaller, but more expensive. Okay, if you're more closer to the CPU, it will be faster. Okay, and it will be smaller because you don't have small in size. Okay, in megabyte or kilobytes, and then but it will be more expensive. Okay, if we go down, then you have bigger memory, but slower and cheaper. Okay, and less access. Okay, the last one is less access. Okay, so we'll see more on the pyramid of typical computer memory hierarchy. And then the basic concept of multiprocessor and multi-core. As we know that now we are gearing toward multiprocessors, or especially multi-core. Okay, so that within one die, one chip, then we can have 2 cores at the same time, 4 cores at the same time, and so on. Okay, The last one is discussing the catch. The principle of locality mentioned that most probably, so we are talking about the probability. Most probably you will need the data closer in time and closer in space. Okay, so that's the principle of locality. Why? So that we, rather than we go one by one, I need this one fetch into the memory, I need this one fetch into memory, you just read in 100 block, for example, 100 elements of that soon to be used memory, and then put it on the cache memory in the CPU, so that it will be faster access. Okay, so that will be the highlight for chapter 1. So now let's see chapter 1. If you have any question, you can interrupt me anytime. Okay, so I need to switch. Okay, so hold on. Yeah, I forgot. Yeah, okay, so I can see you. Okay, so let's continue. Okay, so can you see my screen just to check and hear my voice?
Yes.
Okay. Okay, thank you. Okay, so let's move on. Oops. Okay. Yeah. Yeah. So this is basically the same thing, similar thing that from the study guide. Okay. And also we have something called direct memory access. Means that directly from the I/O into the memory bypassing the CPU. So this is DMA. Okay, direct memory access. So in a way that it will what you call free the CPU utilization, so that the CPU can do other works. Okay. Okay, so let's see here on the Telegram. I put the polls on the operating system. And then I'll see here. Okay, let me retract. Oh, I cannot retract. Yeah. So the operating system I found here just now, 32 has 4, 90% use Windows, 6% use Linux, 9% use Mac OS. Okay, so around how come? Oh yeah, so because this is multiple choice, so the edition is not 100, but you can choose operating system that you are familiar with. Okay, within these 2 years. Okay, because beyond 2 years there are others what you call other advancement that you might miss. Okay. So the operating system is used for exploit the hardware resources, because we cannot use that hardware unless the driver is intact, the driver is plugged in, and the OS also, and it can communicate with the OS. Okay, so that it can be used. Otherwise, cannot be used. It happens, for example, if you install your graphic card and then you don't install the driver, then it will not work until you install the appropriate driver. Okay. And provide a set of service to the system user, so you can have like now the video camera, microphone, maybe printers, LCD monitor, and I'm using also the tablet pen to write down here. Okay, to write down like this. Okay, the other function operating system is manage secondary memory and I/O device. Okay, so this is the basic element of processors. You have this is like a von Neumann machine, von Neumann architecture. Okay, you have processors, you have main memory, you have I/O modules, you have system bus. So this one is popular, I think, yeah, because of the simplicity. So you have processor, main memory, and I/O module, system bus. Then you can interconnect with the I/O modules. Okay, so yeah, so if you can see here, you have CPU or processor. Okay, then you have memory. Okay, then you have various I/O. Okay, and then this one is the system bus. Okay, it can be PCI or DDR4 connected to the processor. So that's why in the motherboard you have north chip and south chip. Okay, north chip normally used for the peripherals like this. Okay, the I/O module, the what's called the system bus. Okay, then the I/O is not limited, so you can connect also to USB, and from USB you can have multiple peripheral, or you can use to GPU card, for example, additional GPU card and additional hard drive is connected to this one I/O. Okay, so let's see one by one. Yeah, so we have, yeah, so the processor is referred to the CPU. So perform data processing function. Now we have, I think, 888, if I'm not mistaken, or 898. Okay. And this is core i9. You have another things. Okay. From Zen, maybe you have Threadripper and so on. So the processor is keep evolving. And the architecture, also you have the difference between CISC, complex instruction set CPU, and reduced instruction set CPU. Okay, so complex mean you can have a complex function within one clock. Okay, it's supposed to be faster, but it will be what you call, it will be the bit power hungry. Okay, it will be power hungry. Or you can use reduce instruction set. So you have ARM processor. This one used in this one Qualcomm. Okay, so this is CISC. Case of CISC, for example, Intel, AMD, okay, and other things. Okay, ARM processor. So this one including the M1 from Apple. Okay, Apple M1 also designed from ARM processors. Okay, and Qualcomm also designed from ARM processor. Samsung Exynos also designed from ARM processor. So they license the design, and then of course then you need to have Silicon Foundry to produce the actual CPU. Okay, the other one that's rising star is RISC-V. Okay, the RISC-V is the rising star. Okay, because it's free, royalty free. Okay, open source. You can say this is open source hardware, so you can build this one. Your special purpose. It has been used also in controlled by Seagate, and so for hard drive and so on. Okay, even can produce what you call something like Raspberry Pi, that in which you can install Linux and so on. And RISC-V already supported by Linux. So this is the growing trend. Okay, and this is also, if I say what you call, if you want like the trade war between China and US. Okay, the China now try to use this one. Okay, because the US block all these things. Okay, the US block all the proprietary license. Okay, but this is open source license. So China already built a good CPU from this one. Okay. Okay, then we have, of course, main memory. So it's volatile. So when you switch off, then it will lose. Okay, the data will be lost. Okay, this is referred to real memory or primary memory. Even from here, you have several architecture. Okay, single data rate. You have double data rate. Okay, double DDR2, DDR3, 4, and then most recently DDR5. Okay, DDR5, and also you have a different form factor. This is DIMM, dual insert memory module, and this is SODIMM, single. This is for laptop. Okay, this is for laptop, and this is for computers. Okay, and the difference is in this notch, so it indicates whether it's 2, 3, or 4, so that you will not plug in wrongly the memory type. Okay. Yeah, so yeah, it depends on the speed also, and also we have another memory type called VRAM. Okay, and this one should be graphic DDR6 and so on. So this is put in NVIDIA and AMD. What was the AMD? The Radeon. Okay, NVIDIA, Radeon graphic card. Okay, you have special design VRAM, video RAM. Okay, it should be faster, because otherwise it become bottlenecks, and then your what you call your advantage of having thousands of CPU cores in GPU card is offset by the slow memory. Okay, so that's why you need to have a faster memory here. Okay, so I/O modules, of course, it provide the interconnection between all the components. Okay, so you can connect to storage, communication equipment, terminals, what you call the keyboard and monitors. Okay, and yeah, see, this is the examples. Yeah, and then this is also an example. What is this? This is Qualcomm. I think this one is Galaxy, Samsung Galaxy something. Okay, the motherboard. So it has the same thing, similar things. Okay, you have the chipsets. Okay, and it connected to various I/O and other devices. Okay, system bus. Okay, you have here. So yeah, you have not. This is not chipset. This is south. Okay, the north connected to memory and so on, and the south connected to other peripheral. Okay, so this is also evolving. You have PCIe, you have PCIe first, another version. USB, you have another USB 2, USB 3, USB 1, 2, 3, and so on. Okay, and also this one SATA, and also for connection to hard drive, you have NVMe. Okay, the SSD card. Okay, for your hard drive and so on. Okay, so what was this? Yeah, so this is the details of the processor. The more detail of the processor, you have CPU. Okay, so you have program counter, memory address register, instruction register, memory. What is B? Yeah, you can see here memory buffer register, I/O, execution unit, multiplication, addition, subtraction, and so on. Okay, and then memory you divide it into two. Of course, you have here 0 to n minus 1 here. So you have 16 gigabytes. So from 0 to 16 gigabytes here. Okay. And then you normally divide it into instruction, and you have the data. Okay, instruction, data, instruction, data. So the instruction will continue here while you are modifying the data. Okay. And then of course you have the I/O modules. Here also sometimes you have also the buffers. Okay, so that you don't do like this, reading one by one and put it here, reading one by one, put it here. You just go directly. Okay, 1, 2, 3, 4, copy directly to here to buffer. Okay, otherwise it will take a long time because you need to interrupt the processor, or if you are using DMA, also you have some time to execute the task. Okay. Okay, so the microprocessor is starting from Intel 4004. You have a complete processor on single chip, including the memory modules, execution unit, and other I/O devices. Okay, so if you have multi-cores, then each chip contains multiple processors. So you have one core, one chip here, and then you have multiple cores. And you can see from here the difference between Intel. So if this one, I think this one will be Intel processors. Why? Because you can see here there's no pin there. Okay, but recently the AMD also starting to do like Intel. So in the way that it will simplify or reduce the cost. Okay, because you just need to put some gold. This is gold. Okay, this is gold. Otherwise, it will the connection is not good. Okay. And GPU, also another type of processor is GPU, but this one, remember that you have the main CPU, still you cannot remove this one, and then you have memory, and then system bus, and then you have the I/O, and all GPU also can be connected to here. Okay, GPU. Okay, can be used, and this is provided single instruction, multiple data. Okay, why is faster? Because it can work on multiple data. Okay, so like say like this one. Okay, you have picture, for example. Okay, and then you want to calculate the the reflection, the shadow for every picture from the light source from here. Okay, so you can calculate, and then single instruction, calculate the shade, for example, and do for multiple data for all the pixel. Okay, so this one is faster. If you go for general CPU, it will go calculate one by one. Okay, one pixel here go to CPU, another pixel go to CPU, and so on. So it will be slower. Okay. So then we have physics simulation for games. Physics simulation like reflection, like what you call like a virtual reality and so on. Okay, or computation of large spreadsheets. Okay, so you have two players type ATI, and also Intel now has what is it called, Intel Z. Okay, this is provided graphic also, and Apple M1 also provide what you call in onboard GPU. Okay, on the Apple chip. Okay, you can add another DSP to help you. Okay, so if there is some DSP command for audio, for like this one, coding for the Zoom, for example, coding the video and audio, the Zoom will use the GPU card. Okay, or you can especially for video processing, you can use GPU card to process the video, or you have also some DSP for analog, and you have DSP for security. okay, for encryption and security. Okay, when you combine all, you have the system on chip. You combine many things. So like this one, regional-based processors. You have network processor and other I/O. Okay, you combine into one. So the one that have processors, memory, and then I/O, you combine into one chip, become system on chip. Okay. Okay, so the learning outcome number 2 is how we execute instruction. So yeah, basically there are two steps here. The processor reads or fetch instruction from memory. Remember here, from memory. So from processors, okay, you have here to memory, okay, and then depending on instruction, can instruct to I/O, can do memory copy, even can do some processing, multiplication, and so on. And then the processor will execute each instruction one by one. Okay, as you recall earlier, the memory is divided into instruction, okay, and then you have here data. Okay, so you fetch the instruction, and then you run in the CPU, and then continue. Okay, keep continue. Yeah, something like this. Start, fetch the next instruction, execute the instruction. If you finish, then halt. Okay. How do you know the next instruction? You are using the program counter. Okay, program counter will start from 1, 2, and continue continuously. Okay, so the program counter is incremented after each fetch. Okay, the instruction the fetch instruction is loaded into instruction register. Okay, so the processor interprets the instruction and perform required action. It can be processor memory related. So for example, load from memory or store to memory, or processor to I/O, like send send the data through Ethernet card, for example, or send to the printer. Okay, this processor I/O. Data processing, like multiply, do summation, subtraction, and so on. Controls mean like if else. Okay, if this one, go to the next one, if that, go to the next one. So this is the control. Okay, so you divided, this is the, for example, 16 bit, so you have optional code. So this is 4 bit instruction. So maximum instruction will be 2 to the power of 4. Okay, because only 4-bit instruction. Okay, and this is the address. Okay, remember address, and then this is the data, the instruction, and this is the data. Okay, so you can have sign and then the 15. So means that maximum will be from minus 2 to the power of 15 to positive 2 to the power of 15. Okay. Yeah, so this, for example, 001, load accumulator from memory, 010, store accumulator to memory, 101, add to memory. So this is hypothetical. Okay, of course, from this also you can divide the instruction. So there's the difference between CISC and reduced instruction set computer or CPU. Okay, so because from the multiple operation, the complex operation from here, for example, I'm not sure, do something, it can be completed by several steps here in RISC. Okay, so that's the idea. Make it a simple. Then what will happen? Then the die size of this is small. Sorry, this one is big. Okay, because of the instruction set. Okay, and the die size of the RISC will be small, so that they can compensate with higher memory. This one high memory, so high memory, so that you don't need to go at the end. It will be faster. Okay, of course, depend on your optimization and so on. At the end, sometimes it will be faster, and also battery is not power hungry. Okay, so you have longer battery if you're using RISC. So that's why the smartphone processors have using the ARM type or RISC type CPU. Okay. The other things on the, hold on, before I move on to instruction, we have some new architecture which is called big little architecture. It's promoted by the, you can see here, the big written as small, little you written as big. Okay, the idea is because of you are using for ARM, for example, ARM processor, you have performance chip, and you have efficient chip. The efficient chip normally is larger. Okay, so that's why, although it's little but larger, because this one will be power efficiency. Okay, power efficiency. Okay, so most of the time you'll use this processor, this core. You use this core, and only when you play game or you do some real processing, then it will activate this one. Okay, so in this case, it will save. And the Intel Gen 12, it will be released, I think, November. Okay, 12th generation. Okay, it will use this big little architecture. Okay, you can learn more this one. I'll put you as assignment later. Okay. Okay, so this is example program execution. You have memory. This is instruction, and this is data. Okay, so this is number one for bits. Remember what is number one? Number one is this one. Load accumulator from memory. Yeah, this one. Oops. Yeah, so this one load accumulator from memory. Okay, and then go to instruction register. And step number two is this one. You load 3 to accumulator. Okay, then the next instruction, the PC go to 302 5941. What is 5? You see what is 5 there? Add. Okay, add with the instruction from 2 to the accumulator. Okay, and then save at the accumulator 5 and continue. Okay, you can see here you read one by one. Okay, and then execute, fetch, and then execute. Okay, so this is how it works. Okay, fetch from memory and then execute at the CPU. Okay, and then okay, number 3 is the interrupt. Okay, why we are using interrupt? So the idea here is we want to improve processor utilization. Okay, we want to improve processor utilization. Why is that? Because as I mentioned earlier, the I/O is slow. Yeah, so this one. Most I/O devices are slower than the processor. I think not all. I think all I/O devices are slower than the processor. Okay. I'm not sure whether they are faster than unless if the I/O itself is, for example, you connected to the one that is faster than the processor. Okay, but most I/O devices are slower than processor. You can name it like printer. Printer, one page, one page per minute per second. Sorry, one page per second. Maybe not 4 seconds. One page in 4 seconds. Okay, so you need to print the whole page, and 4 seconds is one. So it's slower. And then you have a hard drive, for example. Hard drive to access one sector is 100 millisecond compared to 10 nanosecond of reading from memory. It will be slower. Okay, the hard drive will be slower, okay, compared to the memory. Even the memory itself also slower. Okay, so if you see here, you have CPU. You have CPU here. Okay, then normally you have level 1 cache, level 2 cache. Okay, if you have multi-core, okay, you have level 1, level 2 cache, and then combine level 3 cache. Okay, and then after that only you go to the memory. Okay, you can see here how long is that. 1, 2, 3, 4 level of execution. So as I mentioned earlier, this one will be faster but smaller and more expensive. So that's why only small size. Okay, that because it's expensive. Otherwise you and this is what we compensate in RISC processor. Okay, and then processor must pause to wait for the device. If you don't have interrupt, the processor must pause to wait for the device. Okay, and this was full use of the processor. You can visualize like this. Okay, I have execute Word, for example. Okay, Word here. Okay, I'm doing something, and then at one of the time I want to print. Okay, the printing takes long time. It's not enough. Okay, maybe like this. You need to visualize this is 1000 longer than this one. Okay, you need to visualize like that. Okay, so that you can see this is very inefficient. Okay, the CPU usage very inefficient if you don't have interrupt. So if you have interrupt, let's go to interrupt. So of course you need to have some overhead for interrupt. Then go printing. Okay, printing 1000 longer. So at the same time, then you can go back. You can continue with other things. Okay, of course you cannot run Word because Microsoft Word is still waiting for the printing to finish. Okay, you can work for other things. Okay, like using PowerPoint or browse and so on. Okay. Yeah, so yeah, other classes of interrupt. You have program interrupt, you have timer based on time, the IO interrupt. So if finish reading or is there some error, okay, or hardware failure also can generate interrupt. So for example, normally what is what's called always fail is memory. Okay, so that's why you have mem check. Okay, mem check. to check your RAM. Okay, it will generate hardware failure and sometimes directly go to blue screen of dead. Okay, and this is flow control of, without interrupts. So you can see here, yeah, one, and then this is right. Okay, right means you need to go to here. This is without interrupt. Okay, you go for IO program, and then this is the actual IO command. Okay, so you can see from here, but you don't visualize this one like this with this. So you need to again multiply by 1000 here. Okay, longer, like I cannot even draw here. Okay, you need to visualize this 1000 longer. Okay, so this is flow control without interrupt, so it will wait. Okay, 1, 4, 5, and 2. Okay, what if you have short IO wait? So of course IO commands you run up to here. Okay, you need to run this one first. Okay, this is the overhead. Okay, just go to here first. Okay, then run. So while running, the interrupt say that I'm finished. Okay, then the IO command, then interrupt say I am finished. Then you go attend to this interrupt handler. Okay, and then stop here for a bit. Okay, to get the result. Oh, where is it? Yeah, so stop here a bit to get the result, and then you can continue. It doesn't matter, okay, because when you serve the interrupt, okay, so it will save all the necessary before it attend to the interrupt, okay, so that when the interrupt finish, then you can continue as if there is nothing happens, okay. So this is short IO wait. What if they have long IO wait? Long IO wait means you have longer, like printing, for example. So maybe you just need to wait until the next execution. Okay, so if you have longer, what you call long printing, for example, then the program might finish. No need to interrupt the program. Okay, so you have interrupt here and so on. Okay, so yeah, so any question? You can interrupt. You can interrupt anytime. Okay. So otherwise I'll keep talking. So you have here user program. You can see here, this is interrupt occurs here. It's saved first. You go to interrupt handler, do something, okay, then go back here. Then the program can continue as if there's nothing happens, okay. So the cycle interrupt. So you will check the interrupt. If the interrupt enable, check for interrupt. If there's an interrupt, then you go to interrupt stage. If not, then you continue with execute. Okay. Somebody want to talk? Okay, so okay. Okay, let us continue. Yeah, so nothing. Okay, so yeah, this is interrupt. Okay. Okay, so this is programming timing for short IO wait. Okay, so this is the short IO wait. Okay. Yeah, this is without you need to visualize this is 1000 bigger, okay, 1000 longer, okay. So this IO operation processor wait, okay, so 1, 5, 4, 5, and then this is continue. This is the IO, okay, and then you go to 2 and another IO and so on. If you have interrupt with interrupts, then you go to 4. Then you can continue because this one will go in the background. Okay, like you are continuing in the background. Okay, when it finishes, then you can interrupt the number 2. Okay, continue with 5 first. Okay, and then continue to B. Okay, and so on. So this is short IO wait. If long IO wait, that's okay because this one is still longer than this one. Okay, you can use the processor first like this. Okay, you can use the processor first. Okay, but if you don't have interrupt, then you need to wait until the IO finish. Okay, remember, if you can see this 1000, for example, maybe this is around 100. Okay, 10 times slower because you can use for other program. Okay, does not need to wait for the processor to finish. Okay. This is happen if you don't have any other program. Okay, stop but you can continue. Okay, you can continue. Okay, so yeah, so okay, what happen if you have multiple interrupts? So an interrupt occurs while another interrupt is being processed. So for example, you have multiple device and each device generate the interrupts. Okay, let me go first, something like that. Okay, so we need to have two approach. The first one is disable interrupt while interrupt is being processed, or you can use a priority scheme. Okay, So for example, you are receiving a data from communication line like Ethernet and a printing result at the same time. So you will generate at least 2 interrupt. Okay. So the first one is sequential interrupt processing. Yeah, which one is printer? Yeah. So say this is printer and this is the Ethernet. No, the other way around, because you cannot interrupt this one. Okay, the other way around. Okay. Okay, so say this is Ethernet and this is printer, and this is Ethernet. Okay, this is printer. Okay, so what you can see from here, this is if you have sequential interrupt processing. You don't have priority based interrupt. Okay, so if there are 2 interrupts at the same time, for example, the printer need to wait until the Ethernet has finished. Okay, but if you have priority based, you can say that a printer has priority. Please, oh, maybe this the correct one is the other way around. Okay, sorry. The slower one, the faster one can interrupt, not the slower one. Okay, because otherwise it will take wait longer. So this printer, okay, Ethernet. Okay, this is printer. This is to what you call yeah. So imagine this one doing this printing is maybe 100 times slower compared to this one. Maybe this one requires only 1. Okay, 1 second. This one requires 100 seconds to print. Okay, to print let's say 20 pages. Okay, but Ethernet just send the data and then go back, send to memory, and then it can close. Okay, close the communication line. So that's why if it's fast enough, this is negligible. So you can see this is like 100 plus 1. Okay, this is like 100. Oops. Okay, this is like 100 plus 1. Okay, so you just interrupt a bit here, go out for 1 second and go back to the printing. Okay, and yeah, so this is printer. It can be interrupt communication. This is if has this one, the Ethernet, and this has the same priority, so they cannot interrupt each other. Okay, otherwise you'll have different result later on. Okay, but printer can be interrupted because printer is the slowest. Okay. Okay, now let's move on to number 4, which is the memory hierarchy. So we have major concept in memory. We cannot have infinite amount. We cannot have the fastest speed. We cannot have the the expensive one. Okay, we want to as cheap as possible, as fast as possible, and as big as possible. Okay, but we need to have trade-off. Okay, and also memory must be able to keep up with the processor. That's why the memory management unit is built in the processors. Okay, in the processor you have MMU, memory management unit. Okay, so this one will connect to manage the memory. So you have DDR4, DDR5. It depends on the processor. Okay, so if you see now, Intel 12 Gen, they support DDR5. Where do they support from here? The MMU. Okay, is the oldest one can support DDR5? No, because this one already hard coded. Okay, the MMU already hard coded only DDR4. Okay. Yeah. So next one. Yeah. So faster access time, we have greater cost per bit, so expensive. Okay, faster means expensive. Okay, faster, anything you want faster will be expensive. Okay, and greater capacity equal to small cost per bit. If you have bigger, normally it will be when you average, it will be small cost. Okay, it will be cheaper. Okay, bigger, cheaper, and but greater capacity also slow. Yeah, this is the faster access time. Yeah, faster, slower access speed, but the big capacity also normally slower access speed. Okay, so this is the memory hierarchy. You have the inboard memory. Inboard is including registers. This is the fastest. Okay, no other one can fastest. Is including instruction register, memory address register, accumulator, what else? Yeah, so this is the fastest. Okay, it reside in the CPU. And also cache memory, you have level 1, level 2. If you have multi-core, you have level 3. okay, and then main memory, okay, although it's connected using some bus, okay, memory bus, DDR bus, okay, but still this is top of the hierarchy, okay. And you have outboard storage, including magnetic disk, CD-ROM, Blu-ray. So this is hard drive, okay, and SSD may be in here now, okay. And offline storage, this is magnetic tape, okay. This is normally used for backup, okay. Decreasing cost per bit as you go here, it will be cheaper in the percent per gigabyte, it will be cheaper, okay, or per terabyte even it will be cheaper, okay. Increasing capacity, of course, is bigger. Increasing access time, increasing access time means slower, okay. This is mean slower, yeah. So if you go here, magnetic tape, you need to put in a magnetic tape, and then it will run sequentially, so it will be slower, okay. And then decreasing frequency of access to the memory by the processor, okay, means that just used for backup, this one, okay. So it not that what you call frequent access, okay. Okay, so let's move on. Okay, the learning outcome number 5 is principle of locality. So memory reference by the processor tend to cluster, okay. Means that if you are accessing this element of matrix, okay, most probably you will need also the next one, 1 2 3 4 5, okay, most probably, okay, based on the experience, based on the probability, so that data is organized so that the percentage of access to each successful lower level is substantially less than that of the level above, okay. So what you can see here, the principle of locality, right? Remember, just see the example of cache memory. Okay, you have processor. It doesn't matter whether cache 1 or cache 2. Just say the cache memory. Okay, cache memory is attached to the processor, and then you go to main memory. Okay, rather than you access matrix A, for example, 1 2 3 4 5. Okay, 1 2 3 4 5. Okay, you access. I need A1, so you read here, read A1. I need A2, read here, go A2. Okay, what you can do, you can read all the 5 all together and put it here. Okay, 1 2 3 4 5. You put it here. So when I need A1, A2, A3, A4, so you just go here closer to the processor, so you can access faster compared to read one by one. Okay. So this is the principle of locality that has been used by cache. Okay, for any other thing, you have the buffer. Okay, so before you requested, I already have it for you. Okay, so that's the principle of locality. Most probably, we're going to need the data closer in time and closer in space. Okay, so this is A1, 2, 3, 4, 5. Okay, so you read it in one go. Okay, later on chapter 7, we'll see that this is reading is okay, but when it comes to writing, then there's problem. Okay, for example, you have the instruction and you modify this A2 to 4. Okay, but in the main memory still 2. So which one to use? Okay, so you need to make it dirty so that you need to flush. When you flush it, then it will need to update the main memory. So additional work, but still word. Okay, still word. Okay, still you have the effect of faster. Okay, so this is secondary memory. Yeah, so external non-volatile, so it will not lose the information and use to store program and data files. This one is including SSD and hard disk drive. Okay, and cache memory is invisible to the OS, means that the one who manages the cache memory is the algorithm implemented in MMU, memory management unit. Okay, so you don't know what you call the OS is doesn't know how it works. Okay, just instruct something. Okay, but you can see you can see the effect later on. Okay, you can see the effect of the cache memory. Okay, so yeah, so then at least one instruction per cycle. Yeah, so this is the 3-level cache organization. This is single cache. Okay, CPU fast and slow. Okay, so word transfer. This is block transfer. Okay, so you have block here. Okay, and the block have several chunks, for example. Okay, and then this is word transfer. Okay, so yeah, so you divide it again. If this is like this, so you divide it again by word. Okay, then the word can read by here. Okay, by the processor. Okay, you have also level 1, level 2, level 3. Okay, cache memory. Again, this is transparent to the OS, even to the user. The memory management unit of the processor will handle all the updating of all the reading and placement and so on. Okay. Yeah, so it's something like this. Main memory, so you read a block directly. Okay, not one by one, but read a block of memory. So because the principle of locality, most probably you will need the data closer in time and closer in space. Okay. Yeah, so let's move on. Yeah, cache design I'll see later on. So when design the cache, then you need to know what will be the cache size. Okay, of course, the bigger the better, but again, more expensive. Okay, and because it will occupy some die. Okay, and if there is some error in production, what will happen? You need to throw away that processor. Okay, the block size also, do I put in every 5 or every 10? Okay, so you need to have the trade-off there. Okay, the mapping function, the mapping between level 1, level 2, level 3. What happen if the updated in level 1? So what you need to do on level 2, level 3, and even in the main memory. Okay, the replacement algorithm, if the cache is full, because remember that the cache is smaller than the actual memory. So if it is full, then which one to replace? Okay, write policy, if there's some update, so how to update the whole things. Okay, and number of cache level, whether level 1, level 2, level 3, or you need other level of cache. Okay, yeah, so yeah, I move on. Yeah. Okay, the IO, I think I can skip here. The IO, actually they have 3 types. Okay, 3 types for IO operation: program IO, interrupt driven IO, and this is the one that free the CPU. Okay, you don't need CPU to run this one. Okay, you directly copy. So when you are using the DMA, your processors, okay, you have memory and you have IO here. So it not go to P and then go to M, but it go directly from IO to M directly. Okay, copy to the memory, or vice versa, memory to IO directly. Okay. Okay, so the last one is on symmetric multiprocessors. Yeah, so yeah, why is symmetric? Because the early design is like for the server, what's it called, server motherboard, you have here 2 sockets. 2 CPU sockets, for example. Okay, if you want to have dual core at that time, you need to have one core, put it in one slot, one CPU socket, and another one, another CPU socket. Okay, so yeah, so this is symmetric because not necessarily it is the same similar thing, but it can be a bit off. Maybe one is 1 gigahertz, one is 1.1 gigahertz. That still working. Okay, it still can work. Okay, but the best is if you have the similar. Okay, that's why symmetric. 1 gigahertz, 1 gigahertz, and i7, i5, i5. Okay, yeah. So it's 2 or more similar. You can see here of comparable compatibility, not necessarily the same. Okay, not necessarily identical, and share the same memory and are interconnected by bus or other internal connection scheme. So what happened is you have processor here, you go to IO bus here, okay, and then connected to memory here, okay, and processor share access to the IO device, all can perform the same function. Yeah, so you controlled by operating system that provide interaction with the processor. Okay, so the what you call the load is now on the operating system, how to balance the workload, okay, between CPU number 1 and CPU number 2. Okay, the advantage of SMP is performance. Okay, a system with multiple processors will yield greater performance if work can be done in parallel. So there's the if condition here. Availability. So if when failure, so does not hold the machine but still can run. Okay, if the OS is intelligent enough, so it will. If for example you have 2 CPU, if number 2 is failed, so the OS will deliver all the work here. So in a way that it is not, it performs some kind of redundancy. Okay, so it will not fail. It will stop the working of the machine. Okay, but it will slow down a bit because you only have one processor. Okay, incremental growth. So because you can add and also scaling. Okay, you can add in the time. So you buy motherboard with 2 sockets, and then you buy one first, and then you buy one another if there is some requirement. Okay, more customer and so on. Okay. Yeah, so something like this. You have L1, L2, L1, L2, L1, L2, and then you have main memory. You have IO here, go to IO adapter and so on. Okay, so this is if you have SMP. Okay, what's the difference with the multi-core? Okay, multi-core will have, before you go to here, you have L3 cache, the same L3 cache. So this is L3 cache. Okay, you have L3 cache before you go to the system bus. Okay, means that if you want to communicate between processor 1 and processor 2, you can communicate directly to here L3 cache, because L3 cache is connected to all processor, all cores. Okay, no, you don't need to go to memory. Remember that when you go out, it will be slower. Okay. Yeah, so your multi-core computer, so you have here core number 0, core number 2. You can see here, just see this L3 cache. You can see it's occupy 1/3 of the die. Okay, core number 0, core number 1, core number 2, core number 3. Okay, and yeah, so this is L3 cache. L1, L2 is in here. Okay, maybe this one, this fellow, I'm not sure which one. Okay, so you have other units and so on. Okay, so this is Intel Core i7 99X. So you have, yeah, this L3 cache here. Okay, so the difference with Ryzen, also the Ryzen has similar L2 with the adjacent core. So the Ryzen have 512 like this. Okay, 512 like this combined. Okay, so I think that will be it. Okay, so any question for this chapter? So you can ask.